Hi, welcome to Real Learning Center. Today we are continuing with our gravitational videos. We have completed our universal law of gravitation, and then we did a little bit about variation of G, how the acceleration due to gravity varies when you go higher and higher or when you go deeper and deeper into the earth. Okay, now we are going to basically discuss about Kepler's laws. So those are some of the most important laws of gravitation. So we are going to discuss Kepler's laws today. So, who is this Kepler? Okay, Kepler, his name is Johannes Kepler, and he actually was contemporary of Galileo. Okay, and when Galileo was doing a lot of work on telescopes and lots of ideas on how the planets may move and all that, basically Kepler was also working, and he was working with actually. He firmly believed in so-called heliocentric model, in the sense that the Copernicus before Galileo, Copernicus came and said that sun is at the center and all the other planets are going around the sun. So that is called heliocentric model, and he firmly believed in the heliocentric model. He went to actually work with a person called as Tycho Brahe. He was a great astronomer. But he actually did not do too much of analysis. He did a lot of data collection. Years together he did a lot of data collection, and he was very possessive about his data. So he never used to keep. So Kepler actually went and started working with him, doing some research along with him. And Kepler used his data. Actually, at that point in time, I think Tycho Brahe also died, and Kepler took over all the data and started working on for about 10 to 11 years. And he came up with basically 3 laws of planetary movement. So the 3 laws of planetary movements are one of the seminal achievements of basically Kepler. He came with many, he worked on light and many other areas, but these 3 are considered as very important because they are the ones which actually guided Newton to come up, basically match his universal of gravitation and the forces, etc. So that it will actually be aligning with Kepler's ideas. Okay, because Kepler actually used the evidence, the real data to come up with his laws. Okay, so let's see what are his laws. What is first Kepler's law? So let me first state these laws. Okay, Kepler's first law is, so if you take for example, okay, until Kepler, it was all considered that the planets move in a circular orbit, not even planets. Actually, at least Copernicus was saying that planets move in a circular orbit around sun, whereas a lot of other people were still thinking that all the planets move in a circular orbit around the Earth. Okay, so that's called geocentric model. Whereas Kepler anyway accepted the heliocentric model, and then he said that planets actually move around the sun, but not in the circular path. He did a lot of observation of Mars data, movement of the Mars, and concluded that it is not really a circular path. So very hard to do this work, but he finally fit ellipse into that, and he found out that it perfectly works. All the data fits into the model, and he came with this concept of elliptical orbit. So ellipse means which has actually 2 centers. We call it as 2 foci. Okay. So out of these 2 foci, one of the focus on which basically sun resides, and the planet, for example Earth or any other planet, goes around on in an elliptic path. So this is basically his law. His law is very simple. First law is stating that he is making a statement that all planets move about the sun in elliptical orbits, with sun as one of the foci. Okay. So this is his first law. Kepler's first law is quite simple. It goes in elliptical orbit, the sun at one focus, not at the middle somewhere. It is at one of the focus, one of the foci. Okay. So what is his second law? Let's look at what is his second law. So now I'm basically showing you an orbit of a planet around the sun. Okay, and if you carefully watch, it is an elliptical orbit, and let us say sun is at one of the foci. we have just it is slightly what we call exaggerated picture, because generally it is not that much towards the side. Okay, it is other one of the focus, and also the ellipse is not generally very elliptic. It is slightly elliptical when compared to being circular. Many planets. Okay? So it is slightly exaggerated, but however it is on the one of the foci. So you observe here that it is actually quite slow when it is on the other side, but when it is on this side, it is quite fast. The movement of the planet is not constant. It is actually changing. The velocity of the planet is continuously changing. Kepler observed this, and he came up with a law. He can say velocity of the planet has changed, but he came with a law exactly how it is changing. So what is constant here? So whenever you say something is changing, you have to say something else is constant. What is constant? So he came with the second law, and he said that when it is moving, let us say you are going to basically draw, consider some equal periods of time, like 1 day, or let's say 10 days, or a month, or something like that, equal periods. Okay, every month. And for every month, you find out basically out of, let's say, the whole month takes going around. Every month it actually goes by some distance. So you make a triangle from there to the sun, and that triangle area is basically, he calls, is the area swept by the line joining the sun and the planet. So you watch this. So he says that if it is in A at some point in time, let us say it takes about a month, or maybe I will say 1 week to go from A to B, just for the example, 1 week to go from A to B. When it is near the sun, in 1 week it goes from C to D. Now if you actually join that AB points to the center, the sun, and also join the CD points, the area of these two triangles happen to be exactly same. That is what he observed. He calculated all these things. He said the area of these two triangles are very exactly same. So he actually then said with a statement saying that if you see that in equal intervals of time, it sweeps equal amount of areas. So he actually termed in English this statement as a line segment joining the planet and the sun sweeps. It sweeps when it goes like that. It sweeps equal areas in equal amount of time. If you take any equal amount of time, it sweeps equal areas, whether it is near or far. Since it is near, this length is smaller, where the distance that it travels is more. So to keep the area constant, the area is kept as constant, not the velocity. So that is a very surprising thing. It is not going at constant velocity around the sun. It is going around the sun with area keeping constant. So that is a very beautiful observation that Kepler made, and it is his very famous second law. Okay. Later we'll do some analysis of this law and find out why area, how can it keep the area constant? What is it so, what is the sanctity of an area? So we'll figure that out. Okay. So now here he says that the area remains constant. That is his second law. Now let's go to third law. So Kepler's third law. Third law is about, he figured out that the time period for one revolution around the sun is different for different planets, and farther the planets, higher is the time period that is basically observed. But how much higher? Suppose the distance doubles, then how much will be the time period? So he calculated that for various planets, and he figured out a relationship between these two. That means basically the number of days or number of months to go around the planet and the distance of the planet from the earth. He found a relationship between them. If you give one, he can find the other. That is the beauty of this third law. Okay, he stated that when the planet is going around the sun, and if you basically take, let us say, this ellipse, the ellipse, you say this is called as, one line is called as major axis, longer line is major axis. There is no radius here. We call major axis, and minor axis. Okay, and half of the major axis is semi-major axis, and we give it in letter A. We don't use R here. We use letter A, and this is called as semi-minor axis. It's called as V. Okay. Now, instead of giving it in terms of radius, he gave it in terms of semi-major axis, which is A. Okay. So, he gave a relationship between A and the time it takes to go around, time period. So, he said that if orbital period is T and semi-major axis is A, he says, this is his statement. See what statement he made, how much computation he has done for. He worked on for about 11 years on the data to come up with these three laws, fundamental laws. This is the square of the orbital period of a planet is proportional to the cube of the semi-major axis. So, square of the orbital period T is proportional to the cube of the semi-major axis. He came up with this law. So, T square is proportional to A cube. Remember this is Kepler's third law. Always remember T square is proportional to A cube. And this law is very useful to determine the orbital periods of many planets. If you know the orbital period, you can find the distance. If you know the distance, you can find the orbital period. So, they are very nicely related. The T square is proportional to A cube. So, this is one of the great achievements of Kepler. So, now let us look at basically to understand these laws, analyze these laws a little better. Okay. So, let us go to first law and see how we can actually analyze. Now, first of all, we understand today after Kepler went, we understand that things are actually is not just geometrical in nature. Okay. Newton added to that a lot of other things, like for example, what is the cause of motion? There is a force, there is a gravitational force that causes the motion, and the gravitational force actually binds Earth to Sun and Moon to Earth and all that. So, he's figured out all those things later. Okay, so now we have that advantage. With that advantage of knowing Newton's law, now how do we analyze Kepler's law? So, first law, let's look at this. First of all, okay, why this? What is the kind of path that is? He talked about the elliptical path. How does it come about? Let us first. Okay, now this is actually a simple system with two masses connected by, let us say, a thread. Okay, connected by, let us say, a firm thread or stick or something like that. Okay. Now, when you do like that, if they are equal masses, the center is called a center of mass. Okay, we know that center of mass can be calculated with the geometrical center. And if you rotate this, you have some idea of rotational motion. If you rotate this, it rotates around the center of mass, like this. Okay, now even if you actually do not connect them by a wire or a string or let's say a stick, you can connect them by gravitational force. It is there already, gravitational force. If you look at, for example, in the sky, the twin stars, what we call, the twin stars are two stars rotating around each other. If both of them have equal masses, it is possible that they can rotate like this in a circular orbit. They will rotate in a circular orbit, not always. Okay, so you can find twin stars if they rotate in a circular orbit. So this is basically very simply two masses separated by a distance and coupled by gravitational force. So they rotate like this. Now, is it possible that the two masses which are equal, so with the center of mass at the center, okay, can it actually go around each other in elliptical orbits? So that is the question. So the center of mass, what we call in the heavenly bodies, like what we call in the planetary systems and all the star systems and all, this kind of center of mass is also called as a barycenter. So they use the word barycenter, okay, in many astronomical discussions, and Kepler also used to use barycenter. So this center of mass is called barycenter. It goes around the center of mass. Now, if you actually take two, there are lots of twin stars which go around each other, you can see, okay, in elliptical orbits. And these elliptical orbits are still such that if you join at any instant these two planets through a gravitational force line, not planets, stars in this case, okay, and find the center of mass, that center of mass, what we call barycenter, still lies at the center. It doesn't go anywhere. So barycenter never moves, though it goes in an elliptical orbit. What makes some things go in elliptical orbit, some things go in a circular orbit? So that's basically not so easy to say. Okay. However, what we have seen is that it depends on how these two have actually started going around each other. Let us say these two stars were coming from somewhere with certain velocity, and when they come near, suddenly they get attracted. When they get attracted, they also have velocity, so they will start going around each other. Okay. So if their velocities were high, very high, and compared to the distance between them, okay, then they take actually elliptical paths. If their velocities are comparable with basically the gravitational acceleration, that's what we have, gravitational force that provides. There is actually a relationship that we can find out between the orbital velocity and the tangential velocity. So the ratios, if you look at, if they are finely balanced, then you will get circular orbits. Otherwise, you will always get elliptical orbits. Okay, they are more common, elliptical orbits. So shape of the orbit depends on the speeds of the orbit. If the object's initial speeds were higher or lower, it depends on that. Okay. So this is basically equal mass scenarios. Now that is not the scenario of our scenario of a solar system. So what do we have in a solar system? So I am taking basically one single example of Pluto and Charon. Charon is actually a moon of Pluto, okay, and it is sufficiently big. It is not too small. Like the ratio of the masses of our moon and Earth is very high. Okay, so our moon is very small when compared to Earth, whereas Pluto's moon is not very small when compared to the Pluto. So if you carefully watch the path of the Pluto's moon and Pluto, they are actually like this. You can very clearly see that both of them are actually rotating. Yeah, both of them are going around the barycenter. The center one is called as the barycenter. That is the center of mass. They still rotate around the center of mass. They always rotate around the center of mass, and it is very clear here between Pluto, and it's observed very nicely. So Pluto and its moon, we can see that this is how it works. Okay. So what about the sun? So here in this case, one is big and other is small. So both orbit around the same. So if you take this scenario, here you see actually Sun and Jupiter. Yeah, it's still a little bit exaggerated, but Sun and Jupiter actually work like this. Sun is actually not standstill. Sun was actually going around. Sun and Jupiter, if you join, okay, that line, on that line there is a center of mass called barycenter. It is given by a plus there, and that plus is not moving at all. And it just so happens that when it's very big, the center of mass may be inside the bigger body. Center of mass is not outside the body. It is the inside the bigger body. Okay. So hence it goes around like this. In fact, in our solar system, the sun is at the middle, and there is actually there are so many planets. Now with each planet, there is a motion like this. There is a combined center of mass, and everybody is going around that combined center of mass. It's a pretty complex system. Okay. So generally, this when you see from the side, okay, I'm seeing it from the top of the solar system. If you see it from the side, like let's say for example, you are seeing a faraway star, and the star is here, and the planet is going around the star, and you are seeing from the side. How do you see? So you see that the planet is going around the star, okay, and the star is wobbling. We call it as a wobble. Okay, so that is how when you actually look at farther stars, very far, several 1000 light years away when you see the stars. So by looking at the star wobble, you can say that the planets are going around them, and you can compute actually those planets' orbital, how far are they, what are their masses, everything you can compute by looking at the wobble. Okay. That is the beauty of understanding the center of mass and the Newton's law and Kepler's law. Okay. So when one is very big and one is very small, then the center of mass is in between them. And the shape of the orbit again depends on the initial velocity. It could be circular or elliptic. Okay. So this is basically basic understanding of the Kepler's first law. So now let's look at Kepler's second law. Kepler's second law is a quite interesting law. Okay, it is called as it is related to what we call angular momentum. Okay. If we understand a little bit about rotational motion, this is very easy to understand. Now, if you consider this elliptical path and A to B, and it is moving there. Okay. In such scenarios, let's see what is the meaning of, why is this second law telling us that the triangle's area is constant. What is so great about the area of a triangle, and how does it keep that constant? So let us see what does it mean. Okay. So let's take a scenario. How this is the elliptical path, and O is the one of the foci center, and let us take one small delta t time, whatever is the delta t, 1 day, 1 minute, whatever it is. Take a delta t time. Okay, and that delta t time, the planet actually has moved from A to B. So displacement is AB. Planet has moved from A to B in delta t time. So now let's say we will join this and make it triangle. Okay. So what we will do is that we will find out the area of this triangle, because he said that this area for any delta t you take, the delta t being constant if you keep at various other points, this area is same. So what is this area? This area is equal to half into height into base. Okay. So in this case, basically, base is AB and height we have to find out. So let us look at what are these height and the base. So if you see here, actually, I am writing OA and AB. So why am I writing OA? If you take delta t too small and AB very small, okay, then the OA and OB are almost same as the height that you can draw in the middle. Okay, the slight difference is there, but if the AB is very small, then OA is height itself. Okay. So let's say OA is its height. So this is one way of looking at it. The other way of looking at it is basically the area of this, actually this sector, the area of the sector, so you can see, is actually given by the that length is basically arc length, if you calculate, and then also take this angle. So you can also calculate through that means. Okay, now I am taking just a simple triangle area to make it simple. Now, what is this OA? OA is nothing but R. Okay, that is basically our distance, okay, our radius of the path at that instant. That is the radius. Now, if you actually look at velocity of the planet, so in a circular path, velocity is actually tangential to this, and the V is that velocity that we are showing there as a tangent. Now that tangent is the velocity vector. If you take velocity and multiply with by time, okay, V into delta t, we will get actually displacement. So displacement is AB. Okay. So displacement, you can see actually the AB vector and velocity vector are almost aligned. So a slight difference is there. That is because we have taken AB very big to show it. If you take AB very small, that AB vector and velocity vector are aligned. Okay. So the displacement is basically V into delta t. So if you substitute these things into that, you will get basically half into R into delta t, V into delta t. Now what does that mean? area of OAB divided by delta T, I get delta T this side, divided by delta T is equal to half into R into B. Okay. Now, what have we been told by his second law? Kepler says in his second law that the area swept for any given time is constant. That means area swept divided by delta T. As long as you are taking the same delta T everywhere, that is equal to constant. So that is his statement. His statement is area of OAB divided by delta T is constant. Which also means, in our case, we proved that area of OAB divided by delta T is nothing but half into R into V. So we can say in that case, half into R into V is constant, isn't it? If half into R into V is constant, then R into V is also constant, because half is you can multiply it, still be constant. So if R into V is constant and multiply that with M on both sides, okay, then you will get another constant because mass is not changed. So R into V into M is constant. This is another way of looking Kepler's second law. When Kepler says area of the triangle swept by that line in a given time is constant, which means that R into V into M is constant. These two are same. But we know very well R into V into M is nothing but angular momentum, because V into M is momentum. R into momentum is angular momentum. If you have some idea about the rotational mechanics, this is called angular momentum. Angular momentum is constant. That's what it is. So, in essence, he said that when he said second law, he said that it is also called as conservation of angular momentum. So, that is the law. After Newton it came, conservation of angular momentum. That means angular momentum of any system of particles remains same when there is no external force. There is no external force. This is the sun, this is the planet, everything put together is one system. In such a system, the angular momentum has to be conserved. That means it doesn't change. So that is what he is saying. To say angular momentum is constant, since at that time he had no such ideas of the force, gravitational force, etc. He observed saying that the areas swept are constants. Okay. And later Newton said that that is same as angular momentum is constant. Okay. So that is about the second law. Now third law we'll see. So what is the Newton's view of the third law? The Kepler's third law. So Kepler's third law, actually what was it? We'll look at that in a mathematical sense basically. Is, let's say path length is 2 pi r. If r is if there's a planet going around the sun, now I am taking actually circular orbit. So though I could have taken an elliptical orbit, I am taking circular orbit. And my arguments, a circle is a special case of an ellipse. So I can show what it means in a circular orbit mathematically a little more easily than an elliptical orbit. That is the reason I am taking circular orbit. However, it is possible to do the same argument with elliptical orbit. Okay? So let's take circular orbit. So when it is going with the planet is going with the radius r, it means actually that it is going around 2 pi r is its path length, because circumference is circle. So which means basically time period is, if it is going with a velocity v, if it is instantaneous velocity is v, then time period is equal to distance by time, distance by velocity. So 2 pi r by v. So if time period is considered as capital T, then we can say velocity is simply 2 pi r by t. So this is one statement that we are going to make. Velocity is 2 pi r by t. That is the relationship. So we are trying to find out how actually Kepler related these two. Can they be provable by Newton's ideas? Okay. So he said the t square is proportional to a cube, so, or r cube in this case. Okay. Let's see. So Newton says, so there is the force of attraction between the planet and the sun, and that force of attraction gives rise to acceleration, because force gives rise to acceleration when there is mass, and acceleration is called acceleration due to gravitational force. and that acceleration due to gravitational force becomes a centripetal acceleration when already the mass possesses certain velocity. These things we have studied in the rotational motion. So, acceleration due to gravitational force is equal to centripetal acceleration. Now, how can we say this in maths? Okay, we can say that we know that acceleration due to gravitational force is gm by r square. So, gm1 m2 by r square is the force divided by m, which is gm by r square is the acceleration. Okay. And what is the centripetal acceleration? Centripetal acceleration is given by v square by r. That's the formula for centripetal acceleration. Centripetal force is mv square by r. Centripetal acceleration is v square by r. So, if we equate these two, okay, and then v square we know what it is. We know what is v. V is 2 pi r by t. So, substitute it there. So, if you substitute it there and then solve it for t square, you will get it as t square is equal to 4 pi square by gm into r cube. Now, you can very clearly see what Kepler said. What Kepler said was t square is proportional to r cube. When t square is proportional to r cube, the proportionality constant here is 4 pi square by gm. So, this basically we have taken Newton's idea of gravitational force and gravitational acceleration and then arrived at Kepler's theory, which is basically t square is proportional to r cube. And this basically is one of the greatest theories of Kepler. If you actually look at the application of Kepler's third law, I think you get a better understanding of it. Now, moon completes, let us say, one revolution around the earth in 28 days. Assume it's 28 point something. 28 days. If earth had another moon at twice the distance, what would be its orbital period? That is the question. If it had another moon, which is going around the earth, but at twice the distance, whatever the distance of earth is, we don't know the distance, assume. We only know that it takes 28 days to go around. Okay. Now, knowing that if there is a twice the distance, what would be the amount of time it takes to go around? Okay. So, how do we do that? We know that t square is proportional to a cube. That is Kepler's law. Okay. So, we can say that first one is t1 square is proportional to a1 cube. t2 square is proportional to a2 cube. So, you can divide that. When you divide that, you can put equal to, because constants go away. Okay, t1 square by t2 square is equal to a1 square, a1 cube by a2. Okay. Now, we know some values here, substitute it. Given that a2 is equal to 2a1, that means the distance is double, is what we have been told. So, we can substitute that. That means t1 square by t2 square is equal to half cube. This is called a1 by a2 is equal to half. That is why we can say it is half cube. Now, let's solve it for t2. t2 square is equal to 8 into t1 square. So, 8 into 28 square, which is somewhere around 62.7 days. Okay. So, till now we were actually, this t2 square. So, now we take a square root to get that here. Square root is actually 79.19 days. So, we know that when we double the distance, okay, this is actually did not really double. Okay. Square is proportional to cube. So, 28 became 79.19 days. This is how you can actually compute. Given the distance, you can calculate the orbital time period. Given the orbital time period, you can find the distance. So, it's very useful in mapping new planets and planets around new solar system, stars, all that is very, very useful for us. So, now we have completed basically the Kepler's laws, and we have also analyzed them and understood them from Newton's perspective. So, the next step will be to understand how satellites move around the earth and what is meant by orbital velocity, what is escape speed. These are the things we are going to learn in the next session. Thank you.